Alright, so this is section 3.6 on logarithmic differentiation. So let's recall what I showed in the last set of videos, I guess the third video in the last set, that the derivative of the natural log is 1 over x. This really shows that the natural log is a fundamental function because its derivative is something so simple. More generally, if we take the derivative of the logarithm to the base a, where a is a number that's greater than 0, not equal to 1, its derivative is 1 over x times the natural log of a. So this also shows why we really care about the natural log, the log to the base e, because any other natural logarithm gives us more or less the same derivative, except there's this extra factor of the natural log of a there. So this is the simplest logarithmic derivative we can have, or derivative of a logarithm function. Now, I don't really care too much if you memorize the derivative of the logarithm to an arbitrary base a, but you do need to know the derivative of the natural logarithm. Furthermore, there's a really important rule of differentiation that occurs when we apply the chain rule to the natural logarithm, specifically if the natural logarithm is the outside function. We call this logarithmic derivative. It happens so often, it is so fundamental, that I'm just talking about it as if it's a rule in and of itself. So if I apply if I take the derivative of the natural log of g of x, the chain rule says I take the derivative of the outside log of x, which is 1 over x, and I apply to the inside g of x. So that gives me 1 over g of x. Then I multiply by the derivative of g of x, so I get g prime on top. But I don't want you to have to do the chain rule in your head or on paper every time you see this sort of derivative. So let's think of this as just a rule. The derivative of the log of g is g prime over g. In variable notation, the derivative of the log of u is u prime over u. Okay, so let's apply this. Let's take the derivative of the natural log of x cubed minus 1. Well, the logarithmic derivative is the derivative of the inside over the inside. The derivative of x cubed minus 1 is 3x squared, and then I divide by x cubed minus 1. And that's it. Here is another example. Let's let y be the natural logarithm of arctangent x. Let's find dy dx. Again, dy dx is the same thing as y prime, it's just the derivative of y with respect to x. Since this is the natural logarithm of something, we use the logarithmic derivative. dy dx is the derivative of arctangent, which we learned last time is 1 over 1 plus x squared, divided by arctangent. Okay, and I can simplify that to 1 over 1 plus x squared quantity times arctangent of x. A caveat, don't apply the logarithmic derivative if log of x is on the inside, if it's the inside function. So for example, if I take the derivative of sine of log of x, this is not the logarithmic derivative. I need log on the outside to apply it. So when I apply this, I just do the chain rule as usual. The derivative of sine is cosine. I apply that to the inside, which is log of x. Then I multiply by the derivative of the inside, which is 1 over x. And it's not going to be whatever you would think it might be according to the logarithmic derivative. Don't do that. Okay. So here's question 1. Let's let f of x be the natural log of secant of x. Find f prime of x, and please simplify your answer. Make it look as nice as you can, preferably writing it as just a couple of trig functions, maybe even just one. Now I would like us to recall some properties of logarithms. Now these laws hold for all logarithms, but I'm just stating it in terms of the natural logarithm because that's really the only one that we care about. So, logarithms transform products, quotients, and exponents. If I have a log of a product, it becomes the sum of the logs. So I can break up a log of a product into the sum of the two logs, the logs of each factors. It also turns division into subtraction. So the log of a over b is the log of a minus the log of b. The log of the quotient is the difference of the logs. Finally, when I take the logarithm of a power of a number, or an expression or whatever, I can bring the power out in front. So it turns exponentiation into multiplication. So here the log of a to the n is n times log of a. I think of that as bringing the power out in front. That's kind of how I describe it to myself. Okay. Okay, so let's let y be the natural logarithm of x plus 1 over the square root of x minus 2. Let's find y prime. Now, if I was just going to immediately apply logarithmic differentiation, the first thing I would have to do is find the derivative of this inside. And well, that doesn't look like a lot of fun. I mean, I'm going to have to apply the quotient rule and the chain rule on the denominator. It's going to be kind of wacky. So, is there anything I can do to get away from having to do that? Yes, because the things that make it difficult, that I have a quotient and I have a square root, which involves the chain rule, are precisely the sorts of things that logarithms can simplify. Logarithms can simplify a quotient into a difference, and also taking a square root is the same as taking the 1/2 power, and logarithms can take a power outside and front as a product. So, the first thing we're going to do is expand the logarithm. I'll rewrite the inside as x plus 1 over x minus 2 to the 1/2, and then I use the fact that the log of a quotient is the difference of the logs. So I get log of x plus 1 minus log of x minus 2 to the 1/2. Then, this 1/2 power here I can bring out in front. I get log of x plus 1 minus 1/2 times the log of x minus 2. Now, this is completely expanded. I've used my rules as much as I can, and now I'm going to differentiate. And now it is, I'm just going to say it, it's easy now. Y prime is the derivative of log of x plus 1. Well, the derivative there is going to be the derivative of the top, which is 1 over the inside. Excuse me, it's going to be the derivative of the inside, which is 1 over the inside, minus 1/2 times log of x minus 2. The logarithmic derivative of that is the derivative of x minus 2, which is 1 over x minus 2. And so I have 1 over x plus 1 minus 1/2 times 1 over x minus 2. I've simplified that a little bit. 1 over x plus 1 minus 1 over 2x minus 4. You can try to simplify it a little bit more by, I guess, putting it into one fraction, but this is good enough.